Number 8 is a kind of interesting problem where we're doing more things involving definite integrals. We have 3 known quantities. We have integrals of this function f of x, and we're not told what f is. But we know that if we do the definite integral of f from 1 to 5, we get -1. If we do it from 3 to 7, we get 4. And if we do it from 1 to 7, we get 6. So we're asked to find a variety of other quantities about f. So part A says we need to find the integral from 1 to 3 of 5f of x minus 2 dx. So this is the integral that we need to find, and we need to use the pieces that we already have in order to answer this. So notice that none of the 3 pieces that we have are from 1 to 3. But we can use the fact that definite integrals are additive as long as the bounds of the integral match up. So what I mean by that is if the definite integral from 1 to 7 is 6 and the part just from 3 to 7 is 4, we can figure out the missing part, which is what we need for this. So we need the part of the integral that, or the part of the area that's between 1 and 3. So we know that the part between 1 and 3 and the part between 3 and 7 would have to add up to the whole part between 1 and 7. So if the whole part between 1 and 7 is 6, but the 3 to 7 part is 4, we can make the following assumption then, that the part from 1 to 3 of f of x has to be 2. Because these two added together would have to give us the whole part from 1 to 7. So now we can split this integral up in order to solve it. Remember that you can pull any constant you want out of the integral. And if you have a subtraction of functions, you can subtract them separately as different integrals. So the expression in part A that we needed to solve, we have right here as broken down as possible. So notice that this part right here is what we just figured out. And integrating from 1 to 3 of a constant function is just a rectangle, so that would be easy to figure out as well. So this integral 1 to 3 f of x dx is equal to 2. So this is just 5 times 2 minus over here. If you take the integral from 1 to 3 of 2, remember you're saying what's the area from x equals 1 to x equals 3 under the function that's just a horizontal line of 2. So that's just a rectangle. In this case, it's a square that has a height of 2 and a width of 2. So this is, again, its height is 2 because that's what the function is. You're measuring it to the x-axis, and then its width is 2 because it's from 1 to 3. So we get 10 minus 4, which is 6. So part B asks us to find the other remaining parts. We already figured out the f of x from 1 to 3 is 2, so that's here. We also need to find out the part that's 3 to 5 and the part that's 5 to 7. Well, the part that's 5 to 7 might be more obvious first, so I'll do that one. Again, we know that the entire interval from 1 to 7, if we take the area under that, we get 6. The 1 to 5 part by itself is -1, which means then that the 5 to 7 part added to -1 has to give us the whole thing. So this would, the integral of f of x dx from 5 to 7 would have to equal 7, because 7 plus -1 would give us the total of 6. And finally then we can do the part from 3 to 5. So now we can use these two pieces to say that this and this and this all added together has to give us the total interval, right? Because we have 1 to 3, 3 to 5, 5 to 7. All those added together would have to give us the whole thing, 1 to 7. So this is 2 and 7, so that would be 9. In order to get 6, this would have to be -3. So these are all the broken down pieces of this integral. We know their areas without knowing the actual function. So then part C says find the total area between the graph of f of x and the axis. If you are told that f is always positive on 1 to 3 and 5 to 7, and it's negative on 3 to 5. So what that means here is that these integrals from 1 to 3 and 5 to 7, not only is the net area positive, but we're told that function is always positive. So this is the exact area here, and this is the exact area here on those intervals. We're also told that the function is always negative on 3 to 5. So this integral right here, the net area is negative, but that's in fact all under the axis. Like there's no positive part. This is the entire thing. So if you wanted the total area, remember total area, I'll draw a quick example here. If we had a function like this, the definite integral would always give you the top part minus the bottom part. But if we want the total area, we want to add them both as if they were both positive. So the definite integral from 1 to 7 here gives us 6 because we take the positive parts and we subtract away the negative 3. But if we want total area, we want to consider it positive. So basically, we are just going to make this positive. And if we make that positive and add them together, we get that our total area is 2 plus 7 plus 3, which is 12. So remember that the definite integral always gives you a net area. Total area, you're going to have to consider the net parts that are under the axis separately from the parts that are above the axis.
The Teaching Center, UF's Learning Resource Center.